И наш следующий докладчик.
And our next presenter, Professor Mahmoud Sakr, is going to talk to us about the open source project that he's currently working on with his colleague about the MobilityDB. Let us welcome.
The talk is about MobilityDB. It's a database management system for moving object data. Can also call them spatio-temporal data, space-time data. So they have many names. The idea is that you have objects that move on a map, cars, trucks, people, or even ships or air flights. And these objects are being tracked by some location tracking. And you want to store this data in a database and start doing management on them. So MobilityDB is an extension based on PostgreSQL to do this kind of data management. So how does mobility data look like? It typically has this format. You have some identifier for the trajectory, and then you have a sequence of spatial point and time. The spatial point can be 2D or 3D, and the time stamp says when this point was observed. So by doing this, you basically have a set of points. The concept of trajectory goes beyond this because it bundles all the points of a single movement into one composite data object. So here you see it's a point at time and then a second point at time. So this is a complete trip. One is composed in one data item. So we basically connect these points and construct a data item which can be stored inside a relational table, and then you can start doing SQL. Spatio-temporal data requires more than this. For example, if you want to calculate a speed of a trip, of a trajectory, it changes over time because a car can be speeding up, slowing down. So the result of an operator like speed is a temporal float, which is a function in time showing a relation between time and float. You want to calculate a predicate over a trajectory. For example, to say that the speed of trip was greater than 90 kilometers, the result is going to be a temporal Boolean that's sometimes true, sometimes false. So a moving object database system has to also support types like temporal float, temporal Booleans, in order to be able to calculate operations over trajectories. Other variant of spatio-temporal data is instance. So if you want to represent accidents of cars, one accident is just a single location with a timestamp. Or you want to represent the 4 square check-ins of a user. So one user has multiple check-ins that are, again, points at timestamps, but there is no interpolation between them. So they are just discrete. So these are all modalities of moving object data. So what is it all about? MobilityDB has this stack of tools. Looking at the database, PostgreSQL supports relational types, numbers, characters, and so on, and some advanced types, XML and JSON. On top of PostgreSQL, you have PostGIS that provides geometry and geography abstractions so that you can do maps. On top of the two, MobilityDB adds a temporal extension to these base types. So you get types like temporal geometry point, temporal geography point. These are points moving on time, but also temporal integers, temporal floats, temporal text, temporal Boolean, and so on. Why we need this? Basically, to push the data management at the database level. So let's compare how we do a speed of a trajectory in PostGIS and in MobilityDB, or in general in a moving object database system. So PostGIS understands points, but it doesn't understand the trajectory. So you need to put this understanding in your SQL query. So in order to calculate the speed, you need to do some window aggregation, combine every point with the point that comes after, measure the distance, divide by time. So this kind of processing you do in your SQL, so it's at the application level, while in MobilityDB, because trip is a trajectory type, a temporal point, you can directly be calling operation like speed. So this processing is done at the database level. The general architecture of MobilityDB, it's a vertical extension of PostgreSQL. So it starts with the data model by extending spatiotemporal types. There are time types for period set, timestamp set, spatiotemporal types for representing moving points or moving network points. You can have the points represented as absolute coordinates, latitude and longitude, or with reference to the road network. So the point would be a road identifier and a fraction on a road where the location of a car, for example. But also the temporal types like temporal in, temporal float, and so on. These types can be used as attribute types inside a table. And there are also access methods, support an extension of GIST, an extension of SPGIST to support the queries on large tables. The query optimizer is also extended by functions to analyze these temporal types and to estimate the selectivity of the predicates on them. And a big set of operations. For example, you can always project a trajectory, a moving point, into its spatial trajectory, producing a line string and do all PostGIS thing. If you want to additionally process the time, then you use the so-called lifted operations. We call them lifted because they add the time dimension. So you can be doing operations like distance between moving objects. The result is a temporal float. You can be doing azimuth, direction, aggregations, predicates over them, some ETL to load this kind of data. The operations that are supported by the newer OGC standards in moving features are also there. All this is packaged in the extension. Then you can connect through the either by SQL. There is also a Python driver for MobilityDB. You can be using third-party tools like for visualization, QGIS, pgadmin for querying. And because it's an extension, not a fork, it by default is compatible with the tools in the PostgreSQL ecosystem. For example, we have tested with BG routing to convert a temporal point into a temporal network point and to do routing with temporal network points. PipelineDB provides streaming functionality on top of PostgreSQL. So integrating PipelineDB with MobilityDB, you can do some stream management on spatiotemporal streams. It is integrated with Citus to support scalability. There is a Docker image for MobilityDB to start quickly, and so on. So how to load your data inside MobilityDB and start managing them? It's pretty straightforward. It's by doing aggregation. So assume this is a flat table at the left, the trips input. This is a flat table where you can load a GPS track coming from your GPS device, where you have a longitude, latitude, a timestamp, and some identifier for the trip. Yeah? On the other side, you have this table, trips. that contains this TGM point. This is a MobilityDB type to represent a trajectory, and the identifier of the trip. So load your flat data coming from the JSON or comma-separated file into the flat relation, and then combine every latitude, longitude into a PostGIS point, add time to them, creating an instant, a temporal instant, aggregate all instance by the moving object identifier and the trip identifier, aggregate all of them in the array, and then pack this array inside a temporal geometry point. By this, you have constructed a trajectory out of the points. We have developed some ETL so that you can be able to load different data formats. For example, GTFS, this is a standard for public transit for buses and metro schedules. So on the GitHub of MobilityDB, there is a tutorial to show how to load GTFS data inside MobilityDB. Google location data, that's quite interesting. Google knows a lot about us. It tracks when you use Google Maps. Here I know people use Yandex. I don't know whether the Yandex, you can download your location history. In Google you can. And then that's an interesting thing because you look, Google knows a lot already, so you look what you have been doing, in the, what kind of mobility you were doing, were you in, how many hours you have driven, what are the locations you visited, and so on. If you manage to get the location history of someone else, it becomes even more interesting. So I have to warn you, please use responsibly. Another tutorial on the GitHub on maritime data management. This is a location tracking of ships. So these are ships from the Danish Maritime Authority. They publish a huge amount of ship data, ship tracks, and we have loaded them, some of them in MobilityDB, and I am going to show some queries on them. This is a nice use case by Nina. It's going to be the next talk here. So it's an interesting work that she did using the Moscow public transport data, creating these velocity maps using MobilityDB in the back end. Another work by colleagues from Japan who created a visualization tool on top of Cesium to visualize moving object data. So normally this point should be moving. This is one of the ships in the previous slide. And they even do space-time cube, so you can see also the time dimension and the point moving over this line. And this work is actually possible because of the MFJSON standard. This is an OGC, a new OGC standard for the exchange, JSON exchange of moving object data. We are also involved in making this standard. So through this standard, more tools can be supporting mobility data and the exchange. So in this example, we exported this ship data from MobilityDB, imported them in the visualization, and it was possible to visualize them out of the box. So how do the queries look like in MobilityDB? Now we understand what kind of data can be ingested, how to ingest them, but what about the queries? Let's start with this example. We have this table ships, which has an identifier, an attribute trip, a temporal point, a temporal geometry point, and then an attribute speed over ground. This is also reported by the ship tracking. It measures the speed basically of the ship, and because it changes, it is loaded into temporal float. So this is an input data. Also course over ground, this is the direction of the ship. And then I pre-calculate a trajectory as a line string and project this ship into another projection system, the ETRS. This fits the area of Denmark. And now the query is about find all ships that commute between these two ports. So these are two ports in Denmark, and there are ferries going between the two ports. We want to find them in the database. This is an example for spatial intersection. So basically, we use a predicate intersects, which finds the intersection between a moving point and some spatial geometry. If they intersect, this is true. So we want all the ships that have intersected the first port, the geometry of the first port, and intersected the geometry of the second port. If the table is big, which is the case in this exercise, then we want to create an index, an R3 index over these moving points so that this query can be evaluated quickly in a faster way. So this is the result. You have the two geometries of the two ports, and these are all the ships that went in between. Another example to explain more of temporal operations, we want to find the ships that have a speed over ground that is coming from the sensor, different than the speed calculated from the spatiotemporal trajectory. So basically, in this table, we have two speed components. One that is coming from the sensor, and one that can be calculated from the other sensor that reports the location over time. So we can calculate the speed of this attribute and compare it to this attribute. Why we are doing this? It's a way to filter the data, to find noise. Because if the two values of speed are very different, it means that one of the sensors is doing wrong. There is some noise here. So to evaluate the speed of the trajectory, it's the speed of trip multiplied by some number to convert it into kilometers per hour. And this is a temporal float. The result of this first component is a temporal float. And the result of this one is also a temporal float, and then we do a temporal minus. A temporal minus means that in parallel, we scan the two temporal floats and do a minus at every time instant. And then calculate an average of these and compare it to some value. So this is to visualize how things are. The blue curve is calculated speed from the spatiotemporal trajectory. The orange curve is attribute speed over ground. And if we do a temporal minus, we end up with this green curve. And now we want to summarize this green curve in a kind of average. So we do a time-weighted average. This is basically the average area under curve to end up with one number and compare it to 10. So we think that in this query, we think that if there is a difference of an average of 10 in the speed, there is some error. And indeed, we did this and we found noise trips. To show more operations, these are how to do aggregations on spatiotemporal data in MobilityDB. So we want to see the total distance traveled by ships per hour as an indicator of how busy the Danish water is. Is it different per hour, or we have some hours with high traffic, some hours with less traffic, and so on. So the header of the query is just traditional thing. We are creating 24 rows, each one representing a period of 1 hour. This part is a more interesting part. For every hour, we restrict the trip trajectory to this hour. So we get a part of the trajectory. For this part, calculate the length. This is also a MobilityDB operation. And the length is going to give the total distance in meters. do an aggregate of sum, a regular aggregate, divide by 1,000 to be kilometers, and group everything by period, which is hour of the day. So we get something like this. 24 hours per hour, what is the total distance traveled by all ships? There is not much difference, meaning that the Danish water is more or less busy in the same volume all over the 24 hours. But there are also temporal aggregations. This is an interesting concept and a very difficult implementation. If we want to aggregate, for example, multiple temporal floats, let's look how it goes. So what is the cumulative distance traveled by all the ships? Sorry, this is a bit old, another example. What is the cumulative distance traveled by all the ships at every instant of time? So here we use another operator, which is cumulative length of a trip. Cumulative length is going to return a temporal float, which tells at every time instant what is the distance traveled so far from the very beginning of the trip. Yeah? So you get a temporal float that is always increasing. And if you calculate the cumulative length for each trajectory in the table, for each ship, you have multiple temporal floats, and now you want to do a temporal aggregate over them to sum at every time instance, find the sum of all these temporal floats. So again, the result is going to be a temporal float. And it is visualized here. So this is a time dimension, and this is a floating value, and you see that the sum is always increasing, unless for the last part it's a little bit going towards constant. So more or less, the distance traveled by the ships goes in more or less linear, which confirms the previous query, that there is not much difference in the amount of the traffic over time. The last example I want to show is an example for joins. We have seen filters, aggregations, there are also joins, and here we want to look in the database whether there were some dangerous situations where ships came close to one another, so it's a danger of collision. So we want to find ships that came closer than 300 meters to one another. And to do this, we use this operation, distance within. Distance within, it takes two temporal points, the two ships, and the third parameter is the distance threshold. It's going to return yes or no. Yes, if they have ever came to such close distance from one another. No, if they didn't. So for the tuples that fulfill this predicate, for the tuples that have yes, we calculate the shortest line between the two temporal trips. Find the nearest approach where they came closer to one another. This is again spatiotemporal, because assume two ships going like this. Going. So the spatial trajectory is just two lines. So the nearest point is here, actually, if you only look spatially. But if you look spatiotemporal, maybe when this ship came here, the other one was here. So they were not actually close to one another. So measuring a spatial distance is very different from measuring a spatiotemporal distance. So this is a result of the query. The green ships and the blue ships, this is basically the same ships table repeated twice, self-joined. And if one green ship came close to one blue ship, more than 300 meters, we draw this red line between the two. So you see that we have this situation at this area, which is basically the entrance of the port. So that's not very dangerous. Ships are entering the port, so it's normal that they come close to one another. But here maybe it's more interesting because it's happening away from the port. So maybe we want to investigate more and look at their direction when they came to this place, at their speed. Was it to assess more how dangerous it was? Okay, so to summarize this first part of the talk, MobilityDB, it's a moving object database system. It extends PostgreSQL and Postgres. It is developed by a team in the University of Brussels. It's open source, already available on GitHub. We have just released a beta release a week ago. It is compliant with the OGC standards of moving features. There are some ongoing standards in OGC that we are participating in, especially the OGC moving feature access. Moving object data is typically big. A good solution is Citus. There are already many talks about Citus. They're going to be the talk after the next. It's Alicia. Yes. We are using Citus. Thank you for this good work. So by combining MobilityDB and Citus, you can do big spatiotemporal data management. Yeah, so you can deploy a cluster of MobilityDB instances and then manage very big tables. And it's pretty straightforward. One coordinator node and multiple worker nodes. All of them have the same stack: PostgreSQL, Postgres, MobilityDB, and Citus. Few configuration and cluster building statements to create a distributed table, to just mark which table should be distributed, which one should be reference, add nodes to this cluster, and so on. So creating a distributed table would result that the table gets sharded into some shards, and every worker node has main shards and have replicas of other shards in other nodes, and so on. And the good thing is that Citus distributes SQL, meaning that these worker nodes are going to receive SQL statements, and because they have MobilityDB, the SQL will be understood if the SQL has some MobilityDB operations, yeah, which is the idea. Let's show an example. Here we want to do this query. Find all the trips that had length of more than 10 kilometers. Yeah? So length is a MobilityDB operation, and the trip is a MobilityDB type. So Citus is going to break this query in two queries. One query per worker, so assume that the trip table is the one that is sharded over the worker nodes. So every node is going to receive the same query, but only addressing its local shards. And then the coordinator is going to do a union of all the results. So every node will find the trips that it has, which are longer than 10 kilometers, and then the coordinator is going to union all of them. So the thing is that the workers will be able to do this query because they have MobilityDB extension. And moreover, if the query requires using an index, the GIST or the SPGIST extension of MobilityDB, it will be able to do so because it gets planned at the worker. So we have tested this by using a benchmark where we generated syntactic data of different scales and did some workload that is already there in the benchmark for evaluating moving object database system, and the gain is significant. So on a small cluster, we have seen 20 times faster execution. We didn't go to terabytes and petabytes, but then I think Citus is quite capable of doing this. Another branch of development is Python support for Python lovers. There is a driver, a Python connectivity driver to MobilityDB, where you can, the results of your SQL, if they contain temporal data, bring them to Python, do visualizations, use GeoPandas and these packages to do more processing on them, do some machine learning. So this path of applications is supported by this driver. And basically, the Python driver has this class architecture, which is also this is a type system of MobilityDB implemented in C, in PostgreSQL, and also implemented in Python, in the Python driver. So there is this generic type called temporal that accepts some base type. Base type can be integers, so that's going to be temporal integer. Base type is a geometry point, is going to be a temporal geometry point, and so on. Yeah. But then there are 4 subtypes from this base type. One for instant, to represent just a single instant, a single temporal instant. One for instant set, for example, to represent the 4 square example I mentioned in the beginning, without interpolation between the different instances. And then temporal sequence to do interpolation, to represent a trajectory of a person, a car, a ship, or so on. But that's a continuous movement. A sequence is a continuous movement. In some situations, you might need to break the movement and introduce temporal gaps in between. For example, you are driving a car, you go into a tunnel, there is no signal, no GPS signal, so there is no observations. So, and then you exit the tunnel, again the signal continues, and we don't want to interpolate before the tunnel with after the tunnel because we don't know what happens inside. So what to do? Just break the trip at this point, entering the tuple, start a temporal gap. At the end of this temporal gap, again continue the trip. So we just want to put in the data model that in this duration, we don't know anything about the movement. And the subtype to support this is a temporal set. I hope this was not so complex. The whole hierarchy can be instantiated for any base type, for integers, for floats, so you get temporal integers, temporal floats, temporal points, and so on. You can imagine that this is extensible. It can be adding more types. For example, right now we are working on temporal regions. So you want to represent a region that moves over time instead only a point. There are applications for this as well. I'm not going to spend much on how using the Python driver. Just open the connection and start doing your typical SQL, but using the MobilityDB syntax. And now what we want to do next, in terms of distribution, I mentioned already, it's by integrating both MobilityDB and Citus. Works well for most of the query, but there is a little class of queries that is not supported when you want to do non-collocated joins. You want to join, do spatiotemporal joins for shards that are not located on the same node. When you do spatiotemporal joins, you need to shard the data according to some spatiotemporal partitioning so that the shards that are spatiotemporally close to one another should go to more or less the same node in order to reduce the data copying between nodes. But of course, Citus does not understand the MobilityDB types, so we want to add another extension to make the integration between the two and somehow supply this understanding and communication between Citus and MobilityDB to be able to support this little class of queries. But I got to say that this is more scientific. In practice, you don't meet this kind of queries often. We want to do to support multiple versions of PostgreSQL and PostGIS. Of course, you understand how much work is behind this to keep following all these versions. And we want to integrate MobilityDB with more tools in the ecosystem of PostgreSQL, especially visualization. This is our very next step. You can visualize static trajectories in QGIS, line strings, but we want also to start putting some movement in QGIS do more ETL, extract, transform, load, support more temporal types, and streaming. If you want to do online management of online moving objects, right now MobilityDB is not for this. MobilityDB is rather for historical data. You have the complete trajectory, you put it, you have many of them, and then you want to calculate some metrics over these histories. But if you want to do online tracking of moving objects, it's not there yet. So we want also to be supporting this streaming. Two features that, if are added to PostgreSQL, would make our life easier. So I'm discussing them with you here. We would like to see in PostgreSQL something like any temporal. PostgreSQL has pseudo types, any element, any array, and these are basically used to support polymorphic operations at the SQL level. Right now, for example, we have a function called start value to report the very first value of a moving type. We got to implement it 6 times just by copying the same code, only because the type is different. If we can say something like any temporal, then the size of the code is reduced. The problem is that these pseudo types in PostgreSQL are not extensible. It's just hard-coded list of pseudo types. It would be nice to make this list extensible. Another feature we'd like to have is to have a store function. You know, in PostgreSQL, to create a user type, you provide some interface functions, including an input function, an output function, a receive function, a send function. We would like to add to this list a store function. Why? There are situations, and we have a use case, where the memory representation of a type is different than disk representation of a type. PostgreSQL does not make this distinction. It always thinks that the memory representation is the same as the disk representation. So you have your type as a sequence of bytes, and at any time at any point of time, PostgreSQL is going to take this and put it on disk to save the relation. This means that the assumption is always made that the memory structure is the same as the disk structure, which is, I think, in some cases it might not be like this. We have this use case. We want to pre-cache the spatial trajectory with a temporal object in order to be able to do spatial operations faster. Yeah? But then every operation that it changes the trajectory, for example, cutting a piece of it, adding a piece to it, will have to recalculate this cached trajectory, which might not get used. So it's a trade-off between eager and lazy caching, and a trade-off would be to, once we want to store, we calculate. Once it is loaded, it is there. If it gets changed, we don't recalculate. We go rather lazy. Yeah, so to sum up, MobilityDB is already on GitHub. There is a user manual, a detailed one. There is a workshop that's showing all the examples I mentioned in these slides to have step-by-step tutorial. There is a Python driver. Yeah, and that's it. Thank you.
Если у кого-то появились вопросы, самое время их задать. Вот.
If any of you have any good questions, now is the correct time to ask them.
Talk about Python support.
About?
You spoke about Python support, and I have 2 questions. First of all, which is the minimum Python version to work with this?
Which Python version?
Yes.
Huh.
For example, 3.5,
Okay.
2.7, where is this?
I asked
working?
the help of my colleague Esteban, he knows, he did it.
Thank you for your question. We have tested with 3, probably 3.0, but I don't think there will be any problem with lower version like 2.6 or 2.7, but has to be tested. Please contact us if you have any question in this respect.
Okay, I see that any 3.x version will be okay, right? And the second question, let's assume that client which runs Python code is located not on the server side, not on the server, and about to communicate with server, with MobilityDB. Am I understand right? Am I understand correctly that not enough Python model, but we have to download and install some kind of driver, some kind of library in addition to Python model or not?
You need to import the Python, the drivers, the SQL PG, this is the standard driver for PostgreSQL, and then import and register the MobilityDB extension to
It's a
SQL PG.
Python extension, but I'm speaking about extension library for C-written library to another driver for operating system. No?
MobilityDB is not a library, it's an extension to PostgreSQL. So your database is there in PostgreSQL, you create extension MobilityDB, and then you have MobilityDB on the database.
So
And then the interface between the Python and the database is SQL.
Okay. Okay, thank
It's
you.
not a library.
Okay, thank you very much.
Can you tell about 2 or 3 main features what MongoDB or geospatial databases in general want to see in Postgres?
2 or more features that make MobilityDB different than
What you want from Postgres for more?
How make your life easier? I think the question is, yes?
I mentioned these 2 things. They would make the code. This one would make the code easier, less. This one would give us an additional capability to make the memory structure different than the disk structure. Esteban wants to add.
I've tried your library, as you know, and you told about online future. When we use historic data, we can have one track as ready, but in real time, we got point by point. So input of point, it's light query, but if we make track online, it will be update, or how will you realize it?
Okay. So the question is about how to support streaming, to summarize. The problem is that trajectory is a long structure, is a big structure, and if we keep appending points to this long structure, it's very heavy operation. So the solution that we want to investigate, we are not yet there, is to do a kind of lambda architecture, where in the online part, this temporal inst is used, not a complete trajectory. A temporal inst is just a single point. And then these points get cached and in patches get added to the trajectory. So it would require some integrating multiple pieces together. But I don't think we can do better than this because database systems are quite different in their architecture and concepts than data stream systems. So in order to support both, one needs to build an architecture that combines the two functionality.
Hello.
Hello.
Thank you very much for really interesting presentation and really amazing tool. I can't wait to try it hands-on because we do a lot of like traditional ways of interpreting trajectories of moving objects. So my question is, you had one of your first slides was the traditional structure for storing these kind of data. So we are also working with ships and ship trajectories, and usually we need not only timed this temporal geometry, we usually have some more data to store with it. For instance, if it's maybe trajectory of a ship, we should have some additional data, like maybe how much, for instance, how much fuel is on the ship right now, and so on and so on and so on. In traditional structure, we have only one column representing date, and lots of different columns. Do I understand correctly that we need to create lots of temporal fields in the database? So effectively, we are duplicating the date column. Is there a cost to volume of the table? Thank you.
Thank you. Very interesting question. And yes, your understanding is quite correct. This is a case shown here, for example. The trip, the speed over ground, and the course over ground all share the same time dimension, which is indeed repeated on all of them. So you would like, as an optimization, to have the time only once and all the data attached to it.
Maybe if we could, also you had a slide when you had temporal anything. Maybe if we could have this record type with geometry and lots of integers and floats and make it temporal, maybe it would help or something like that.
It would help to store the data, but what kind of operations you can do there?
Yes, of course, yeah.
You need to have operations operating over these types, and these operations need to understand what is inside the type.
So
it cannot be that open.
Actually, it's the cost of operating. So we make, maybe we could make our database less normalized and bigger, but we will have faster operation. That's what I understand.
So just a note, so this moving object database topic has been studied in academia for more than 20 years, and these models are really built with care. MobilityDB brings this to end users. So this part of data modeling, I didn't see before, that to combine everything in just a pseudo type, and I don't believe one can do meaningful stuff over there. So in order to support functionality and genericness, you got to repeat this temporal dimension. But that's an interesting point. Let's discuss offline. Thank you.
Sorry, I just wanted to answer your question that with respect to the feature that we would like to have in MobilityDB to help us our life. As we partially discussed yesterday offline, indeed sharding is a very complex issue. So we are working on extending the parallel planner of Citus to work to better do a spatio-temporal sharding of the data that preserves locality and diminishes the transfer of data from one node to the another to do spatio-temporal joins. So any idea in these parallel distributed queries, it's indeed more than welcome in our current development status.
Я думаю, что на данном этапе нам уже...
I think that this is the stage where we have to finish up, but any questions that you have remaining, you can ask them personally. You can ask the speaker personally. Thank you very much.